Howdy everybody, this is Sanjay TJ from Monster VTU. Alright, now, today we're going to discuss about the topic alternating current and circuits, #1, that is part 1. So in this video, as a brief, we're going to discuss what is AC, that is how AC power is generated, the principle, and then we're going to see what is Faraday's law, how do you do it, and with a small video. And we're also going to look about the Lenz law with also a small video. That video is highly interesting. Alright, without no further delay, let's go forward, shall we? So the generation of AC, they have taken a very simple basic model of two bar magnets, one which is in North Pole, the other which is in South Pole, and then in the middle is the copper plate. So what you see here is a magnetic lines of force, also known as magnetic flux. So we have a video coming up, so we'll go for that straight away. Here, one way to generate an AC voltage is rating a coil in a magnetic field. So here, the B field is constant and the area of the loop is constant, but the angle between the field and the loop is changing. The voltage oscillates from positive to negative. Well, you see, the voltage oscillates from positive to negative. That is, you see this blue dot which is going from positive to the negative. And this is the representation of the sinusoidal AC voltage. So it is constantly going. This is the most simple way to generate an AC voltage. So this is the basic model of what you can get in the process of generation of AC. That is alternating current. This is the galvanometer, and this is the shaft, and this is the circuit connection. And thanks for watching this video by the author. Well, I also have this a YouTube description down here, so you can copy this and paste it in your web browser, which is included in the description box below, and you can enjoy the videos here. Right now, let's go for the next one, shall we? Now, what is AC voltage? First of all, a very basic question we have to understand. So in this, we have three kinds of voltages. One is the topmost, which is represented in blue color, is the pulsating voltage. You see it has only positive half cycles, and then you see the direct current, which is very straight. It's also known as the direct current, which we studied in the DC circuits. Yes, and we have the alternating voltage, which is the AC. This being the zero and this being the highest peak. I'm sorry. It is known as the topmost level of this green line is known as the thrust, and the bottommost line of this green line is known as the crust. So this is the topmost point which an AC voltage can reach, and the crust is the highest point a negative cycle can reach in an alternating AC voltage. Now, so a voltage supplied by a battery or another DC source has a certain polarity, and it remains constant. Here we see an AC sine wave, and we see that it is constantly changing, going negative or going positive, and then negative, and then positive, and so on. So it is alternating, so that's why alternating, and we have this A, and this is current, so alternating current. So finally to the Faraday's experiment. So let's just see what What did he do? Well, he took a galvanometer and a coil or a loop. It is like a cylindrical in shape, but it is in coils, and you have a hollow space inside. And what is this? Is a bar magnet of uh, a north pole and a south pole. So when this magnet is moved to and fro, that is inside the loop and outside the loop, that is inside the hollow cylindrical part of the coil, and outside when it is taken inside and taken outside, there is a deflection in the arrow in the galvanometer. So as a theory, how it goes is like when a magnet is held stationary at that position, the needle of the galvanometer returns to zero position. So now, when the magnet moves away from the coil, there is some deflection in the needle, but in opposite direction. And again, when the magnet becomes stationary at that point, respect to the coil, the needle of the galvanometer returns to zero position. Similarly, if the magnet is held stationary and the coil moves away and towards the magnet, the galvanometer similarly shows deflection. It is also seen that the faster the change in the magnetic field, the greater will be the induced EMF or voltage in the coil. So this should have been in the first place, that is in 1831, Michael Faraday. Behold the Michael Faraday, an English physicist, gave one of the most basic laws of electromagnetism called Faraday's laws of electromagnetic induction. One of the basic, like it is the basic of the basics. Like if you have that, you can construct based upon that. If you don't have that, that's really tough. So thanks to Michael Faraday, and during his experiment, he found how EMF is induced in the coil when a flux is linked with it changes. So, what is the conclusion that we draw from this experiment of Faraday's? Is that, well, from this experiment, Faraday concluded that whenever there is a relative motion between conductor and a magnetic field, the flux linkage with the coil changes, and this change in flux induces a voltage across a coil known as EMF, or the electromotive force. Now, let's come to the two laws which Faraday concluded about. He said that any change in the magnetic field of coil of wire will cause an EMF to be induced in the coil. This EMF induced is called induced EMF, and if the conductor circuit is closed, the current will also circulate through the circuit, and this current is called induced current. Well, there are some terms and conditions that apply to this too. That is, the method to change the magnetic field is either by moving a coil towards or away from the coil, or by moving the coil into or out of the magnetic field, or by changing the area of a coil placed in the magnetic field, or by rotating the coil relative to the magnet. Okay. Now, we are going to see a small experiment that is being done on the Lenz law. This is seriously, you have to go to this link. I'm sorry, I have provided this link in the description box below, so you just have to go there and click on it, and then you get this video. This is absolutely wonderful.
And it's a paramagnetic material, so essentially it's non-magnetic. So this magnet has no effect on the copper gas. And this is a rather strong magnet, and it's a D-cell battery, which is several times heavier than the copper, but it's easily picked up by this magnet. So now what I'm going to do is I'm going to take this magnet towards away from the copper gasket. And what you'll see is the copper gasket starts swinging. Now, on the
Or let's go for the Faraday's second law. I'm sorry the video is being prolonged very much. I'm sorry, I have included some videos, so the I have to spend time. So let's go for the Faraday's second law. It states that it states that the magnitude of EMF induced in the coil is equal to the rate of change of flux that linkages with the coil. The flux linkage with the coil is the product of number of turns in the coil and flux associated with the coil. You have two definitions in here. That is, either you can go by the first statement, that is, it states that the magnitude of the EMF induced in the coil is equal to the rate of change of flux that links with the coil. Or you can also go for the law that states, both of the law are same, just different English words. That's it. So the second version of the Faraday's second law says that the flux linkage of the coil is the product of number of turns in the coil and flux associated with the coil. Okay, so we will see how the working of a EMF takes place here, shall we? Yes.
EMF, or electromotive force, refers to the voltage created by a battery or by a changing magnetic field. Counter EMF, also called back EMF, is a related phenomenon that will illustrate in this animation. There is a simple circuit featuring a battery, a switch, and a light bulb. This circuit contains a wire coil served as a conductor. Conductors or magnetic field generates around the current passes through. They are called inductors. EMF opposes the change that created it. In this case, the change is the cessation of the current. So, opposing this change, the back EMF wants to continue its gain, which turns once again to the pole, causing it to flash, or it fades away altogether.
Alright, I have included the the YouTube box, the description of this link in the description box below. Right? So let's move on. Well, seems like we have to crush some papers. That's it. Thank you. Thank you for staying with me so long. And that's it.